Thanks for introducing me. Thank you to the organizers for having me. A little bit inspired by Vivian's talk earlier, I'm going to talk about something that is not a priori a non-crossing partition story, but I think it will appeal to some of the people in this audience. In particular, we're going to see a lot of the tools that we've been using this week to develop machinery, and so I hope that it will inspire thoughts in you guys, and maybe you'll solve some cool open problems. This is sort of another poset topology talk, but it's a story about Möbius functions and also about non-negativity. So these are words that I've been hearing throughout the week from sort of both sides of the probability and pre-probability / combinatorics folks. So I hope it'll be fun for everybody. There's sort of three places you can find what I'm going to talk about. So we have an archive post. It was published, I think it was technically published December 20th, 2024, but I think 2025 is somehow how it's listed. That's the journal version, and then there's also a FIPSAC extended abstract, so if you want to see the 12-page short version, it's there too. This is joint work with Joshua Maglione and Christian Stump, who's running around somewhere there. Okay. So I'm going to divide this talk into three parts. I'm going to start by telling you what why are we doing this. It's a problem motivated from number theory, and I'm not really a number theorist, but I Josh, who's one of the co-authors, thought deeply about this and came up with a conjecture, and I'm going to try and report to you guys what he told me and explain the important things that they wanted to understand, and then in the remainder of the talk, I'll sort of show you the combinatorics that we use to prove their conjecture. So part two of the talk will be the main objects, where I talk about these polynomials that I'm going to show have non-negative coefficients. And I'm also going to talk a little bit about some of the tools that we use to do that. And at the end, I'll talk about the actual concrete results. So not just what we were playing with, but actually the things we proved. So for the motivation section, we're not going to become experts on this particular field, but I want to give you a sense of the kinds of questions that were being asked and the kinds of things that would be a good answer. So in the 80s, these three guys were interested in these things called subgroup zeta functions, sort of like some kind of generating function coming from a finite group or finitely generated group. And then a couple of years later, there was some machinery developed to actually compute these things using p-adic integration. And one of the questions that people are often interested in has to do with finding the poles of these zeta functions. So 2 years ago, Maglione and Voll started looking at a special case. These things are difficult to compute, but you want to understand their poles. So they said, okay, what are the simplest few cases we can think of? I think the simplest case is technically a product of monomial, a single monomial, but they looked at a product of, so the input of these things is a product, or is a polynomial, and they looked at a polynomial that factors into linear factors of the reals. So their input polynomial for these things is a product of linear things, and when they were doing these p-adic integrals and doing certain substitutions to sort of simplify things just to sort of get to the guts of what they actually want to compute, they find that the information that they want to collect from these integrals depends only on the geometry of the zero set of this product of polynomials. So this is going to be telling us about the combinatorics of the intersection of a hyperplane arrangement, but it's really the zero set of these polynomials. In particular, they do a very natural substitution in so they end up with this rational expression and many, many variables. They do some sort of natural substitution and simplification, and they realize that once you get down to these two variables, the rational expression has only one pole t equals 1 with some kind of multiplicity. And they make a conjecture about the multiplicity of this pole and its relationship to the combinatorics of this hyperplane arrangement. So just to say, the goal of this talk is going to be, they have a conjecture about the multiplicity of some pole of some rational expression. We're going to prove their conjecture, but the way we're going to do it is kind of silly. Well, not silly, but it sounds like we're going to do something with rational expressions. What we're actually going to do is just look at the numerator of this rational expression and show that it's not 0 when t is equal to 1. And the way we can do this is by showing that the coefficients are all non-negative. So the point that I'm sort of getting at with this numerator story is that one of the main objects is going to be a combinatorially defined polynomial, and it will turn out, although it's not immediately obvious, that it's like in order to prove this non-negativity result, we're going to use some tools from poset topology that we already saw in Mathieu and a little bit in Katharina's talks this morning. And after we wrote this paper, Christian Stump realized that there's actually a connection between these polynomials that we've seen before and Chow rings of matroids. These are having a little bit of a moment right now, so I want to shout out, if you're interested in them, check out Christian's paper about, which it's quite a long title, but the first couple words are Chow and augmented Chow polynomials as evaluations, and then it talks about this extended AB index. I'll tell you about it. Okay. So that's sort of like my motivation section, and I want to tell you about the actual combinatorics of what's happening here. So for the purpose of this talk, I'm interested in finite arrangements of hyperplanes. So what that means is I take affine linear subspaces of codimension 1. I've drawn affine in gray because I'm going to tell this story for the case where all of those subspaces are truly like linear subspaces, meaning they pass through the origin. This whole story works if you allow, so on this right-hand side, I have H1, H2, and H3. They all pass through the origin in R2, which is that intersection. You could move H2 down, and then you end up with a triangle in the middle. And what I'm telling you today will also hold for these affine arrangements. But I'll need to be a little bit more careful in how I set things up, and there's all this stuff about like the intersection poset's not a geometric lattice, blah, blah. There's all these things that I don't want to get into, so I'm going to simplify the story in the talk. But if you're interested in seeing how it works for affine arrangements, I'm happy to talk about it afterwards, or it's in the paper. Okay, and I want finitely many distinct hyperplanes. So this is coming from the zero set of a product of linear forms. So in principle, you could have a product like two linear forms that are the same linear form. When you pass to the combinatorics that we're going to care about, we're not going to be able to actually see that difference. So I'm only going to care about like distinct finite collections. I'm going to be focusing on the intersections of these hyperplane arrangements. So you have this collection, and they're real hyperplane arrangements. They're sitting in R to the D. And I want to look at sort of non-empty intersections of some of the hyperplanes. We saw this in Emily's talk already, but just so that we're on the same page, because there's many ways to think about this. We have, in this particular example, we have the intersection of none of the hyperplanes, which is R2, and then any of the singleton hyperplanes, H1, H2, and H3, and then the intersection of all three of them. And it's clear from this picture that if you have the intersection of H1 and H2, that's the same subspace as the intersection of H2 and H3, which is the same subspace as the intersection of H1 and H2 and H3. I'm going to arrange this collection of intersections into a poset by reverse inclusion. So that means I'm going to start with R2 at the bottom, and then in this case, I have the intersection of all three hyperplanes at the top. And maybe what's interesting to note about this poset is that it's very well studied in the hyperplane world. So one of my favorite theorems is the theorem of Zaslavsky from the 1970s, where he shows that there's a relationship between the Mobius functions, the Mobius function values of lower intervals of this poset, and the number of regions of the arrangement. So just to see what this looks like, we've seen Mobius functions quite a lot in this conference so far, but just so we have it in our head, I'm drawn next to each of the points in this poset the Mobius function value of the lower interval. So in this case, it's the interval like R2 to R2, and in this case, it's this interval, like this number corresponds to this interval, that number corresponds to this interval, this number corresponds to this interval, and that up there, well, okay, I added up all these numbers and flipped the sign, and that's the two. And I claim that if I take the absolute values of all these numbers and add them up, I should get the number of regions here. So this is the number of, if I delete the hyperplanes from R2, in this case, there's some number of connected components, in this case 6, and I call these things chambers. let's just check, there's 6 of these, and indeed 2 plus 3 plus 1 is equal to 6. So like Zaslavsky sort of gives us to this, and this is already hinting that there's some relationship between geometry and combinatorics of these posets. And so I'm not going to tell you too much about how this geometry and the combinatorics of the posets fit together, but just to tell you that this is like a sort of natural thing to do, and there's lots of reasons why this is a reasonable approach to take. So one of the ways that we sort of collect information about these posets is with the Poincaré polynomial, which is just the generating function of the absolute values of these Mobius functions. So all I've done is taken the absolute values of these Mobius functions for these lower intervals, and I've stuck a y where I'm keeping track of the rank in the poset. In this case, it's something geometrically defined, and so I can really talk about the codimension of the vector space. Okay, I have some words up here like central and essential. This sort of just saves me time in this way of writing it, but just think about this picture. Sorry? It's a little bit important. So, but also the signs aren't that important because they alternate. When you have a geometric lattice, the signs alternate. So like, yeah, okay, yeah. So the reason, I guess, maybe the reason I like the absolute, okay, so let me finish the sentence for those of you who are not on the same wavelength. And geometric lattices have this property that the Mobius functions alternate by rank. So when you make like sort of another thing that you could have, a different polynomial you could have made would be to just drop the absolute value signs here. And then if you plug in a -1, you get sort of the same coefficient sequence, but yeah. I would say it's more common. I guess I particularly like, I'm just gonna forward this, I particularly like this version because it tells us about like the Hilbert series of a graded ring. I'm not gonna talk about so I'm a particular fan of the Orlik-Solomon algebra and the Marchenko-Gelfand ring, and if you take the associated gradient of the Marchenko-Gelfand ring, you get the Cordovelle algebra. And the fact that the coefficients are positive means they're actually counting the dimensions of things. Also, okay, also the number theorists found this polynomial in the wild and they didn't have signs in it. So we could have changed it. So what Christian is asking is also about the characteristic polynomial. The characteristic polynomial is very similar to this, but you reverse the order of the coefficients and you keep track of the signs. This is also something people care about. It's a specialization. These are sort of all specializations of the polynomial, which is also another polynomial that people like to study in the context of matroids. So these are all sort of various aspects of the unfolding world of matroids that sort of you can give different perspectives on that tell you different pieces of useful information. Just to keep it clear, here are 2 posets and their Poincaré polynomials. So this is the one on the bottom that we just computed. It's a 1, 3, 2, because we had 1 and 3 things there, all with -1 is the Mobius function, and then a +2 at the top. And the higher up one that I can't really reach with my hand, all of the Mobius function values here turn out to be plus and -1. So in this case, it's just the number of things at each rank. When we talk about rank, we'll see this, I'll say this more formally a little later, but the point is these have a unique minimum and maximum element because they're central hyperplane arrangements, and all the chains between that minimum and maximum have the same length. I think we've seen this a couple of times already in the talk. Okay, so I also want to point out that this statement about minimums and maximums and the maximal chains having the same length, it's really a statement about graded posets. So it's not super important. This is a hyperplane arrangement that we're getting this from. And in fact, sort of one of the things that I'm going to highlight in this talk is that the geometric lattice wasn't super important, but like other aspects of graded posets were like somehow the important key observation. I'm now going to show you a definition that requires some explanation. Oh no, I'm going to recap. Oh, I moved this. Okay, sorry. Throughout the week, I've been like removing slides from this talk because people have been introducing things. And I thought that I had removed this slide because I think several people have defined a graded poset. So I'll just say it briefly, which is that so we know that a chain in a poset is a subset of the vertices of the Hasse diagram, or the poset elements, the ground set poset elements that are totally ordered with respect to the partial order. And I'm particularly interested in maximal chains. These are ones that if you have, oh, actually, what do I say? In my case, my posets are going to always have a 0 hat and a 1 hat. So this is minimum element and maximum element. And I'm particularly interested in the setting where these graded posets, where so these maximal chains, when you can't add anything in from 0 hat to 1 hat, always have the same length. I'm also going to be interested in intervals in posets. I don't know if we've seen these already, oddly enough. These are just, you choose 2 elements and you look at all the things that lie between them, inclusive. So that was how I was doing this lower interval calculation when I was computing the Mobius function earlier. But it doesn't have to be lower intervals because, of course, there's other kinds of intervals. So this is an interval in that poset. So now I'm ready to show you something. Oh, this should be a P. I see a typo. These are P's here. I haven't changed the L's to P's. So I want to describe you as like sort of chonky polynomial that is going to be the main protagonist of this talk. It combines a bunch of other polynomials that you might have seen before. So this Poincaré polynomial, as well as the AB index. I don't want to focus too much on like the actual details of what this is, but I will explain to you sort of what it is, and then I'll give you an example. So this Poincaré polynomial is, there's an extra parameter called, which is C in there. So the point is you sum over all chains in your poset, well, you remove the 1 hat for sort of technical reasons, which I can say in a minute. So you sum over all chains in your poset, and you want to look at the product of Poincaré polynomials. So we know that for every interval in your poset, you can define these Poincaré polynomials by doing a second sum over all the elements in the interval. And then you can take a product over the intervals between things in your chain. This is some kind of weird product of polynomials determined by the chain. Any chains, all chains, yeah. Just go ham on your chains. If you did maximal chains only, it would be products of 1 plus y's, but then it gets more interesting when you're allowed to have like intervals where weird things happen. So this is a polynomial in Y, and it's a product of stuff. And there's some formal constraint where maybe I'm going to always add the 1 hat into the chain. So like once you stop your chain, it finishes the poset for you. I'll show you an example. And this weight here, this is keeping track of the ranks that you, so this is a polynomial in A and B, which are non-commuting variables. And it's intended to keep track of the ranks that you used in your chain. So it's not just a monomial in A's and B's, it's a monomial in B's and A minus B's, which you should think of like either you used something in that rank, or you didn't use something, but you could add it. So the B minus A's, you should think of like, if I added something of that rank, then I would pick up a minus sign in my sum, but this is going to give us some kind of inclusion exclusion. I just want to sort of flash an example at you. So this has slightly boring chains, I apologize, but I want to show you I've written out a poset, and all possible chains in this compact form, and then all the Poincaré polynomials, all the chain Poincaré polynomials, these product of Poincaré polynomials that you get from these various chains, and then I wrote down what ranks were being used in each of the chains, and then these weights. So I want to highlight maybe this bottom row for a second, partly because that's the one I can reach. So this bottom row here, it's chains of the form 0 hat, and then one of these 2 things here, alpha 1, alpha 2, alpha 3. So in our geometric picture, these are the hyperplanes in that arrangement of 3 hyperplanes in R2. So maybe I'll draw it again. And these chains are just, you take the bottom element, and you also take one of these things. So what's a little bit silly with these other chains is they're just one element or no elements. And so what we're seeing is you have the product of the Poincare polynomial of this interval, which is 1 plus y, and then I'm sort of forcing artificially to complete the chain to the top, so I get a product of 1 plus y. And that makes it a different polynomial than if I just took like one of these guys and not the 0 hat, because then it's just like a 1 plus y on its own. But the difference between these two things is that when I record the ranks that I'm using, in the first case where I'm using the 0 and the 1 rank, I get a b squared. And then in this one where I'm just using something in this first rank, these hyperplanes, and we get an a minus bb. So we can think of it like I didn't use the 0 hat, but I could add it and give myself a minus sign. Okay, I'm gonna stand closer to this. But I could introduce a minus sign. Okay, and they're non-commutative, so that's really helping us keep track of like what the ranks are. It did not already exist, but it was given to us by the number theory in the sense that the numerator of this rational expression that I mentioned is a bivariate polynomial in y and t. And by understanding somehow, like when you set a equal to 1 and b equal to 2, you recover their polynomial sort of on the nose. I mean, it's close enough to give the right theorem, but this is an easier to explain thing for a talk. So the reason that this refinement is here with these a's and b's is so that the combinatorics works out better. Sort of the machinery inside the proofs is slightly more refined than their version with the t's. Yeah, right. Like somehow you have like this inclusion exclusion, and you want to say like if you're using these specific ranks, this happens, instead of just like you're using like here you're using one rank, you're using one rank. So if you're just keeping track of like the power of t, so instead of having you'd have like a t and a 1 minus t, and then a 1 minus t and a t. Like these are indistinguishable if you use that specialization. But if you use this further refinement, they're no longer distinguishable. Or they're not distinguishable. Yeah. Yeah, it's the Mobius function. Let's say you had a3. It's the Mobius function of this interval. Yeah. I don't want us to get bogged down in like really deeply understanding this polynomial, just that it's some like sort of complicated polynomial you can study, and that I want to prove things with it, and I want to prove that it's non-negative coefficients and use this to solve someone else's conjecture. I'm of course happy to talk about it. I'm like really jazzed about this polynomial, but I think it's very hard to sell to other people unless you like have a motivation, and my motivation is going to be let's solve an open conjecture that a bunch of people tried to work on and couldn't solve, and this gives the solution. Great. Am I on time? Great. Okay, great. Just to give us, I'm just flashing this again. Here's a different poset and its extended AB index. You'll notice that the coefficients are non-negative. Maybe something to observe. Great. Okay, so just to keep this story honest, the conjecture from Maglione Voll, this is a sort of restated version, but it's what I sort of just told you. If we can show that this polynomial has non-negative coefficients for geometric lattices or intersection posets of real hyperplane arrangements, then we will have proved Maglione and Voll's conjecture. And the purpose of this talk is that we can prove their conjecture and that the proof holds for a much larger class of posets than just these intersection posets of arrangements of hyperplanes. And maybe your favorite poset is one of these. Let's actually talk about what we did. This I actually get to skip a little bit of because Katerina gave us like a lovely explanation about R-labeled posets. But just to remind us, we've seen a bunch of posets where you label the edges of the Hasse diagram with various things. In this case, I want to label them with numbers, and I want to ensure that when I look at any interval, there should be a unique weakly increasing chain. Sort of the magic of R labelings in our context is that the number of decreasing chains in each interval tells you the Mobius function values. So like when I'm telling you about our labels, the reason that I care about it is because I care about using those Mobius function computations and telling us about chains. I'm not going to read this whole slide because we already know all about this from the last talk. And I just want to point out that there's a theorem of Fjorner from like 1980 where he proves that geometric lattices have R labelings. As a bonus, we saw this in some of the other talks, or sort of in a related bonus, non-crossing partition lattices also come with R labeling. So these are things that you might already be excited about. This is like one of the main pieces of machinery that we're going to use to understand these polynomials. If you are a poset topologist enthusiast, you might know this theorem, or just a simplicial complex shelling enthusiast, you might already know that one way that you prove non-negativity of the H vector is by using properties of shellings, and somehow this should be a very reminiscent story to that. So the theorem is just, this polynomial is non-negative, and we can use techniques inspired by poset topology to prove it. And I'm giving you an explicit, manifestly positive description of this polynomial in terms of monomials and some generalized descent statistic. The idea is that you look at maximal chains in your poset and you shade some of the edges, and these shadings then correspond to turning the labeling from a positive number to a negative number. This updates what your descent set should be. And if you sum over all of these, you get like a cancellation-free formula for these extended AB indexes. But you really need to know information about this R labeling for this whole machinery. This, in particular, immediately implies Maglione and Voll's conjecture. And it means, and like our surprise bonus from before is that if you hadn't, like there's more posets than just geometric lattices. Like there's many, many more posets that admit these R labelings, and perhaps your favorite poset does too. I just want to give you a quick, again, I'm just going to flash an example, but what I want to point out is now there's some extra data. So you have maximal chains and somehow subsets of the edges. And just by coloring the edges and updating the descent sets by flipping like a 1 to a -1 when you color an edge, you get this new description in terms of y's and monomials in A and B. And if you sum across in the appropriate way, you get this nice formula that doesn't involve any minus. Now I get to highlight another new result that someone else has proved and use it to motivate a question for you guys. Recently, Hoster and Stump, so that Stump, but his grad student, Elena Hoster, have a better pair of statistics in the case of partition lattices. They're particularly interested in the setting of the braid arrangement. So I'm describing this in terms of like these shaded edges E and maximal chains, and they have some other way of interpreting these objects that is sort of bespoke to the braid arrangement. It has to do with permutations. I am not an expert on that paper, but someone in the back is. So there's like settings in which people, sort of what I say is like there's interesting settings where you might be able to get, like this is sort of an abstract thing about like maximal chains and generalized descent sets, and it did solve our conjecture, but it'd be interesting to know if there were sort of more statistics that are a bit cleaner or more natural that show up for special posets. So like, does your favorite poset have a particularly good version? In particular, like we were motivated by geometry and the geometry of hyperplane arrangements, but this seems to be something that exists beyond geometry, and I would love to know if there's some like particularly good meta reason for this thing to have non-negative coefficients that doesn't rely on our labeling's work. Our labelings are sort of a fickle thing. Okay, that's, I think, all I wanted to say to you guys. Thank you so much for listening.